Hello, my name is Sam Berridge. My student ID is 106511696. I was given exercise 26 for the viva as coursework. This question asked me to take these 6 matrices, check if they form a group together with matrix multiplication as the binary operation, and also give an isomorphism to a group we encountered earlier. So first off, what is a group? A group is a set G, so here's my set, together with a binary operation circle. In this case, our binary operation is in fact matrix multiplication, not circle. And check that it satisfies the following axioms. So our axioms are closure, identity, inverse, and associativity. So start off with closure. So what is closure? For all G and H within G, G circle H should also be within G. So we can check this on the Cayley table. So here is all my elements of G, and here they are again. And within the Cayley table, they should all be elements of G, which they in fact are. Pause it and have a look. Next up, identity. So there exists an identity element E within G such that for all G, G circle E equals E circle G equals G. So our identity element is obviously going to be this guy here. We know this from previous work with matrices, but we can also see it in the Cayley table again. So our identity times any of these gets back these lot here, which you can see. And again, any of these times the identity element gets back these lot here, gets them there. So next up, inverses. So what is inverses? So for all G, element of G, there exists an inverse element G inverse, such that G circle G inverse equals G inverse circle G equals E. So these 4 right here, these 4 are their own inverses. Again, we'll see that in the Cayley table. So well, obviously E is its own inverse, but I'll show you just E times E gets back E. But for this one times this one gets back E, this one times this one gets back E, and this one times this one gets back E as required. And then for the last 2, these 2 are inverses of each other. Again, see it on the Cayley table. So this one times this one gets E, this one times this one gets us E. Final axiom is associativity, and we know matrix multiplication is in fact associative. So G with matrix multiplication is in fact a group as it passes all 4 axioms. Next on to the isomorphism. So what could the other group be that it is mapping to? Obviously we have to choose that ourselves. I've chosen this guy, I've chosen the symmetry group of a triangle. So what is an isomorphism? That's important. What is that? So an isomorphism from a group to another is a homomorphism, which is 1 to 1 and on to. The next thing is to choose our map. So our identity element, of course, has to go to the identity element in the other group. This is our other group again. But what about these other groups? What about these other elements? Sorry, why did I choose these elements going to the other elements? Well, I've decided that, I thought about it as this first row, I called it A, this second row I called B, and this third row I called C. So in this one, A and B are swapped around, and this is the same case here, where this symmetry transformation will swap point A and point B around. Same with S, so this is going to swap C and B, S, swap C and B. T is A and C, T clearly shows that A and C swapped. The rotation is a bit more complicated, so we'll start with A down here. So what does A do? Well, it's a rotation by 2 pi by 3 anti-clockwise, so that means A is going to go to B, B is going to go to C, and C is going to go to A. Is that the case here? Well, where does A go? A goes to B, seen here. B goes to C, and C is at A. Great. B, same case, so 4 pi by 3 anti-clockwise. So obviously different case, but rotation again. So B is going all the way to A is going all the way to C, and C is going all the way to B. Should be able to see that there. Just for interest of time, I'll skip it. So next up, we need to prove it's an isomorphism. So to do that, we need to prove that it's a homomorphism to start with. So what is a homomorphism? So a homomorphism from group to another group is a mapping such that for all G1 and G2 within G, we have this equation here satisfied. I've checked that for all 36 options. I'll show you each one. So here's 1 to 6. Here's 7 to 13. Please pause it when required. 14 to 20. 21 to 27. There we go. 28 to 34. And 35 to 36, so that should show that is in fact a homomorphism. But next time we need to show it is 1-to-1 and it is onto, so it is 1-to-1 since every element in the symmetry group has only one element in G that maps to it. Again, we can see that with the original mapping, that each element within the symmetry group has only one element in G that maps to it. Is onto, since every element in the symmetry group has an element in G which is mapped to it. Again, you can see that here. So here's all the 6 elements. Each one has one that is mapped to it. So therefore, it is an isomorphism since it's a homomorphism that is both 1-to-1 and onto. Thank you very much.